So let's get into the material for today. So we're going to just do a bit of motivation today for optimization. Presumably you guys are already somewhat motivated because you've shown up for this course. But it doesn't hurt to kind of be explicit about what we're trying to do in this course anyways. And we're going to get to a bit of basic convexity at the end. So we'll jump into that stuff at the end, and then next lecture, which is going to be Thursday, we're going to be doing a kind of much more thorough lecture about convex functions and convex sets. OK, so optimization problems, I claim, are kind of ubiquitous in statistics and machine learning. They kind of appear throughout these two disciplines in terms of the estimators we form, the problems we're trying to solve, et cetera. So in many stat and machine learning courses, like let's suppose you took 707, regression analysis in statistics, or you took 701 or 702 or 715, these types of courses, they'll often teach you about how a certain conceptual idea translates into a particular optimization problem. And you don't really talk about the optimization component that much. Maybe you do a little bit more in a class like 701 or 715, but you more learn something like, let's suppose I want to fit a linear function to my data, but I want to impose some kind of structure on the coefficients in that linear function. Like maybe I want the coefficients to be sparse or something. Maybe I want them to be shrunken or something. You learn how to take that conceptual idea and how to translate it into an actual optimization problem. Right? So you take, or another example might be classification. Right? You want to maybe fit the best hyperplane with the biggest margin to separate two classes. You learn how that idea translates into a particular problem that you solve in order to achieve that goal. Let's just go through some examples of this. I kind of already verbally said a few, but I think it's fun to do this to see what examples people think of. What are examples of particular cases in those two disciplines of kind of statistical learning goals that you can translate into optimization problems? You don't have to raise your hand. You can just shout them out. Okay. Minimize the loss function. OK, that's kind of like a meta example. That's really what, I'm looking for something more specific. Let me just already put down the two I mentioned. So there's regression and classification. And let's get even more specific. Let's suppose we just do least squares regression. That's a very specific example of a problem, right? We're trying to minimize the least squares loss. Say to fit a linear function of some target y on some features x. Classification, I kind of mentioned some SVMs. That was kind of what I was referring to, let's say. OK? Other examples. What are other examples? Yeah.
Preference ordering.
Preference ordering. So I don't really know what you mean by that.
You have a similarity function and two data points that are supposed to be similar, and another data point that is more dissimilar than the other one. So you optimize that your similarity function, your scoring function, scores the similar one higher than the other one. So
it's kind of like a ranking problem, it sounds like.
Kind of, yeah.
So that's interesting, because that sounds to me like probably a discrete optimization problem which is not convex. At least I imagine that's one way that you can formulate that. But that's an interesting example too. Let me just add that both of these can be done with regularization of sorts. In fact, SVMs kind of have that built in already, right? So that means we can do least squares subject to some kind of extra regularization, maybe to make the coefficients shrunken or sparse or something else. There's a hand here I think I missed, yeah.
I want to say for regression, you mentioned regularization means lasso.
Right, yeah. So that's an examples of types of regularization may be L1 or L2, which at least in the context of regression we would call lasso or ridge. Other examples, there are lots, yeah. Solving a linear system, yeah, we do that a lot, but why would we do that? Let's see if we can come up with a specific. So I'm asking a really silly question though, but which is why would you solve, what linear system would you want to solve in statistics or machine learning, or another field if you're in a different field.
So when you do like regression, you can think of it as solving the equation.
Right. I'm asking, just give me a kind of concrete example of what y and x would be there. Or b and a if you're solving this system, right? So there's linear systems, which are in a sense more basic than all of these. So we'll write it as b equals ax, or because I'm a statistician by training, you guys will be subject to my notation for the semester. I write that as y equals x beta. What would give me an example of what these would be. Just anything.
So the A can be a model, and X can be a data set, X and B.
So, sorry, this one.
So X and Y can stay for data set.
Yeah, okay.
So B as a model, try to.
So these could be like model features or something, and this could be a target. I mean, this is like doing regression without noise, right? I guess I was just looking for specific example because linear systems are so kind of ubiquitous, but I think that's fine. We can leave it at that. Other examples. What's that?
Resource allocation or clustering.
Yeah, resource allocation is an interesting one. Again, depending on how that's formulated, that may not be in a convex problem. Clustering is also an interesting one because clustering is typically never convex when it's formulated. There are a few convex formulations. We're throwing out these words convex and non-convex. I assume people are kind of familiar with what that means, but we'll make it precise at the end. And also sometimes, now we're getting into kind of a second set of examples, sometimes clustering is not even formulated in terms of an optimization problem. It's just a procedure. You do these steps, you end up with a certain set of clustering assignments. OK, so let's actually, that's a good segue into the next set. What are some non-examples? Which means examples of things that you may want to do in these fields that actually don't correspond to an optimization problem at all. And these are, I think, typically harder for people to think of. I'm going to just assume that you guys were shy, which is why we didn't fill out 2 pages with examples, because I know that you guys all know a lot more. I'll make clustering precise here. K-means clustering is an example of an objective we try to solve. Right? It's non-convex, so we do it in an approximate way to get a certain set of clustering assignments. What's an example of a way to do clustering that's not actually given by the solution to an optimization problem, but rather it's given by the output of an algorithm? It's another one of the really basic ways to do clustering. Right, hierarchical clustering. It's really just the output of a sequence of steps, right, of an algorithm. Hierarchical clustering. What's another one? You guys maybe learned this in 702. I think hierarchical clustering is kind of close to optimization because at every step there is some sense of an optimal choice, right, of the way to split things up. Still after, say, like 5 steps up the tree, it's not actually solving a particular optimization problem. What's another one? Yeah, that's a good example. So density-based clustering is really very far away from clustering, from optimization problems entirely. So in density-based clustering, we fit a density to our data set, right, which is kind of more descriptive than a set of clusters. And then we look at level sets, or maybe say super level sets of the density to form clusters. So we say, let me look at everything that has a density higher than, say, 0.7. And I'm going to look at the connected components of that, and I'm going to call those clusters. Something that's becoming popular now. Other things that are not optimization problems that we do. Yeah, that's a good example. So tree-based models, like decision trees, for example. It's kind of tricky, right? So you could maybe kind of argue that's an approximate solution to a non-convex problem, right? Because it's like a greedy way to solve a very difficult problem over the space of trees. So we'll kind of put a half there. Maybe that's inspired, in a sense, by an optimization problem. It's too hard to solve. Certainly something like density-based clustering is not inspired by any optimization problem. What are other examples? These are actually like harder to think of. It's the point we're trying to make here. PCA. So that one, I'm going to put that one in between. PCI claim actually is the solution, so the principal component, say the top k principal components that you get out of some data matrix, that actually is the solution to an optimization problem. Believe it or not, a convex one, even though you typically learn it in a non-convex way. And we'll see that either in a few lectures or at the end of the semester as a kind of interesting example. Although we typically think about it sequentially, there is actually a single criterion you could write down that would give you, say, the top k principal components. So you could think about it in either way. Yeah? Boosting, yeah. So that's another one that I'd say is kind of like a half. That's following from tree-based models. People think about boosting in different ways. People from the CS learning theory side of things tend to think about boosting as in some kind of game theoretic way. People from the more stat kind of flavor of ML think about boosting actually as an additive model. So it's something that actually does kind of solve some optimization criterion in a greedy way. So we'll talk about boosting when we talk about gradient descent, so you'll see that perspective. Yeah?
Monte Carlo-based methods add random number translation.
OK, so yeah, Monte Carlo-based methods, these are getting to be really kind of tricky how to interpret them. Sometimes you may be running a Monte Carlo method to solve a non-convex problem, right? So it depends what the inspiration is coming from these. But yeah, there are certainly things that don't have anything to do with optimization that we do, like something to do with random number generation. That's right. It's kind of far away from optimization. Let me put down two just to conclude our list that I think are things you guys all use, or at least are all familiar with in some sense. Cross-validation and bootstrap, I think, are two premier examples of things that are very far away from optimization problems. Let's suppose I told you, I want an estimate of the test error. Here's a classifier. I want an estimate of the test error. You could use cross-validation to estimate the test error. You could use bootstrap. Those are two things that I think, at least for people in stat and ML, are very natural, right? But they have nothing to do with optimization criteria. The cross-validation estimate itself, right? The estimate of test error you get for a particular, particular function or a particular training model you've built, it's not optimal with respect to any criterion. It's just given by a sequence of steps. You split up the data set into different folds, and then you train on some of the folds and test on the other, and you rotate around, etc. And same with bootstrap, right? The bootstrap estimate of test error, say for a particular, let's say, classifier of the misclassification rate, that's not optimal with respect to some criterion. It's just that these two things are very natural, and kind of our understanding of them seems like they're a very, very reasonable things to do, which is why we tend to trust them a lot, even though we don't understand much about them. I'd say in terms of relating them to like a particular optimality criterion. OK, that was just to get us thinking a bit. So why are we going to bother thinking about the right-hand side explicitly, right? So we talked about various examples of things that translate into optimization problems, a few things that don't. This class, we're going to be thinking about the right-hand side in particular. So we're really not going to be doing this kind of translation from left to right very much. We're going to assume that you've seen that in other courses. We're going to be opening up kind of the black box that this right-hand side is, and we're going to be figuring out details about this problem, which we'll call P, how to solve it, and also why it's important to recognize that certain problems can be posed as optimization problems. So presumably, you can go into R or MATLAB or Python. These things typically have built-in optimization routines to solve big classes of problems. And on your first homework, you'll use kind of a disciplined convex programming language that can almost solve any convex problem that you want to formulate. So given that's the case, why would we actually bother with trying to think about how to solve this problem, which is going to be the focus of this class? So I have kind of two motivating reasons I want us to keep in mind. The first is that different algorithms for solving particular problems, they can perform better or worse depending on the flavor of problem. It can even be the same problem that you're trying to solve, but just a different instantiation of data. Maybe it's just the data comes from a different distribution, so it's of a different nature, but it's actually the same problem you're trying to solve at a meta level. Or it could be that the problem that you're solving is very similar to, in appearance, to another problem that's you're trying to solve, but algorithms that are effective for those two problems are very different. Okay, so we're going to see an example of how different algorithms can perform kind of, in a pretty drastic sense, better or worse for a particular problem in this lecture. So that's important to know, and it's also important to recognize when that's the case so that you don't have to rely on kind of this black box solver that may at some point fail if you try to solve a problem that's large enough in scope that it becomes really impractical to use a poor algorithm choice. The second one is a more subtle reason. I think most people will kind of, they were aware, you're aware of this at some level, even if you don't know how to solve the problem, you're aware of it at some level. The second one's more subtle, which is understanding how to solve the problem and things about its nature in terms of kind of, let's say, optimality and different kind of views that you can take from the perspective of convex analysis can actually lend a deeper understanding to the statistical side of the problem in the first place. Or let's just say the side of the problem that's the conceptual side. So it's a bit subtle, but sometimes understanding how to solve a problem or understanding things about it that seem to be purely optimization-related quantities, they can actually influence the way you think about the problem outside of optimization. Whether you're coming from ML or stats or engineering or something, can actually influence the other side. And we're gonna see an example of this also in this lecture. Optimization is a very current field, so it moves very quickly. Even if I look at my lecture notes from 4 years ago versus today, a lot has changed in optimization since then, and so we've kind of actually changed a lot of the advanced topics. A lot of the core materials stay the same, but there's quite a fast pace in optimization in terms of what people view as important and relevant. So that can be intimidating, right? If you enter a field where things move so fast, and maybe it's a bit intimidating because if you feel like you really understand something, next year at NIPS people might say, oh, that's old news. We're done with that. Now we're on to this. But that's also very exciting. And that also reveals there's a lot of room for progress. It's really wide open in terms of people being able to contribute really meaningful things. And that's not true in older disciplines, right? Even I'd say CS and statistics in some sense they have more kind of classic, there's more of a classic kind of lay of the land in terms of what you learn when you take the intro courses. An intro to optimization course, in large part, can be really influenced by what's happening today. So there's a lot of room for progress. I think that makes it a very exciting time to take optimization, especially at the interface of statistics and machine learning. So let's go through this example and as a motivating example for why different algorithms can work better or worse for different problems. And this is a particular problem we're going to try to solve. It's called the 2D fused lasso problem in statistics, but in signal processing it's known as 2D total variation denoising. And it's usually actually referred to as anisotropic total variation denoising to differentiate it from the isotropic version, in case people are familiar with that, coming from, say, image processing. So the setup is we get a bunch of observations. We'll call them yi, from I going from 1 to n. And we're going to envision them as lying over the pixels of an image. So imagine I just took this image, and I think this image is something like 300 by 150 pixels. And I just unraveled those pixels in column measure order. So this was y1, the pixel right below it was y2, et cetera. And I unraveled it, and I got a big vector that was 300 times 150 long. That's yi. That's my data. And I'm going to interpret different values of y, so the different values that are assigned each pixel, in terms of some color scale, just visually to help us. So the values go between about 3 and 7. And I've taken some kind of true image here, which I've plotted in this first column. And I've used the color scale. And then I've added a bunch of noise to it. So I've actually just taken these true values, and I've added a bunch of Gaussian noise to it. I'm going to call that y, my data vector. Okay, and so you can see that the truth was kind of blocky in the sense that there were blocks of the image that are all the same color. This noisy version, it doesn't have that blocky structure anymore. Okay, and so maybe we were doing some kind of compression, or maybe we were observing this image over a channel that was noisy. Just imagine that for some reason we have a noisy version of some true image, and our goal is to denoise the image. So it's to get a blocky representation of the original image, but just going off of the data. We obviously don't see the truth at all. So to do that, one way to do that is to solve what we sometimes call the fused lasso or total variation denoising problem over the image. And it's given by the solution to an optimization problem. That optimization problem is actually fairly simple, and we can write down the criterion and intuit what it's going to do. So for every pixel in the image, we're going to assign a coefficient. So for every yi, there's going to be an estimated coefficient, which we're going to call beta I. Again, I'm a statistician, so I tend to call model parameters beta. And so we're going to choose those parameters, the estimated level at every pixel in the image, by solving the following optimization problem, which is a minimization of a criterion that has two terms. The first term is just a data fitting term. So I'm going to want to make yi be as close to beta I as possible for every I in terms of a sum of squares sense. Okay, and if all I had was this term, then the solution would be trivial, right? I just would estimate beta I to be yi for every I, and I would get back the data. So that wouldn't be very good. The second term is going to give us the desired structure of the image. It's going to try to enforce that blockiness that we want. And that's given by what we might call a fused lasso or total variation penalty. And essentially what we do is for every pixel in the image, we just penalize the absolute difference between that pixel, the value of that pixel, and all of its neighbors. So imagine I'm going to take every pixel, I'm going to look at its value, I'm going to look at the value of the pixel one up from it, one down, one left, and one right. And for each of those differences, I'm going to add a term in the penalty that's their absolute difference. That's what this is doing right here. Beta I minus beta j for every I and j that are joined by an edge. And we're thinking about like a grid graph here. So edges occur between pixels if they're adjacent horizontally or vertically. Hopefully that makes sense to everybody. Okay? And if you've seen sparse regression before, which you've seen lasso probably if you've taken 701, a lot of other classes, you can kind of recognize that the nature of the sum of absolute values as a penalty is to force some of the things inside the absolute value to be 0 exactly at the solution, as long as this parameter that's multiplying the penalty is large enough. So the same thing is going to happen here. If we make this penalty parameter lambda large enough, then at the solution we're going to get exactly beta I equal to beta j for many pairs I and j. And which ones are set to 0 exactly, which differences is going to be determined adaptively. So this was an example of the solution at a particular value of lambda. I just chose that value of lambda for visual purposes to make the solution match what we know should be the true image. Okay, so you can see that it is really blocky, as you might expect. Yeah, a question, two questions.
So how is the political to taking care of the difference of betas only between the nearest neighbors or the edges? Is that just one particular example of many possible penalty terms that can be?
The answer is yes. So the question was, is this the only reasonable thing to do in an image kind of denoising example, or are there other reasonable things to do? There's lots of other alternatives. So this is, like I said, called anisotropic total variation denoising. It looks at the sum of the absolute differences, the sum of those across every neighboring pixels. The isotropic version of total variation denoising would actually group horizontal and vertical differences together and take the L2 norm of those differences. Not the squared L2 norm, but the L2 norm itself. So that, in other words, what that's doing, and we may get into more details later if we touch on this as an advanced topic, that tries to make simultaneously vertical and horizontal differences equal to 0 at a pixel. This tries to make them just equal to 0 individually. Right? This penalty has no preference if you do a bunch of fusion in the vertical direction but not in the horizontal direction. It doesn't really matter to this penalty, right, because they separate. The isotropic version tries to make differences that occur in the horizontal and vertical direction 0 simultaneously. And there are lots of other examples of taking larger neighbor sets.
Like having, in that case, I, j, instead of that being an element of the edge, it can be an element of the open wall or something like that?
It would be something like this. So where you see, let's actually index beta by the x and y coordinates, just so it's clear. It would be something like this. So right now, we're just looking at if I add 1 to the x index or add, oh, thank you. You guys have to remind me because I may forget occasionally. If I add 1 to the x index or I add 1 to the y index, we're just penalizing the absolute difference between these two. right? That's what the penalty is looking like right now. That might be a penalty term, right? And we're going to see another penalty term for this guy as well. That's the anisotropic version. The isotropic version would actually take this as the penalty. Okay, so if you haven't seen group lasso type stuff, then this may not make as much sense, so don't worry about it. But I just was kind of claiming, at least, that this is going to try to enforce differences in the vertical and horizontal differences to be 0 simultaneously. So that you can talk to me after class if you're curious. Yeah, you had a question.
So there's a disk underneath the sea, and then I see a leak on one side between the disk and the sea, and not on the other side.
Here, you're saying?
No, go down and to the right, top. Sorry, the bottom half of the sea.
Bottom half of the sea, yeah?
Yeah, so now go up a little bit and to the right, you see that, yes. And
Yeah.
you don't see that on the other side.
Yeah. So you're saying this kind of gets smeared a bit.
Yeah, a lot more than the...
Uh-huh. So I don't really have a good answer for why that happens. The question is why? Or yeah, I mean, to be honest, this could just be the particular instantiation of noise made these levels look higher in this particular example. So we could rerun this and see the opposite or not see it at all. I don't really have a smarter answer for that. But this does kind of relate to the next point we'll make after this example, which is that spurious jumps or spurious kind of structure in the solution actually happen quite often in these problems, and they're almost unavoidable. So it's a good question leading into the next one. Yeah.
Could this be related to the fact, or maybe to the observation, that this regularizer is not very good at boundary points? Because you're trying to minimize the differences.
Do you mean it like shrinks differences? What do you mean by boundary points?
Like in the boundary points, the colors would change dramatically, and they would be different at
Uh-huh.
boundary points.
So certainly part of this is due to that. So we're penalizing every difference here, right? Not just ones that have to do with that should be 0, right? So what we're seeing, if you look carefully, is that this blue is actually a little bit less bright than this blue. This red is less bright than this red. This pink is a little less bright than this pink. They all get smushed towards each other. That's because everything is being penalized. So even though we know these differences should be non-zero, the difference between this level and this level is going to be smaller in the solution than it is at the truth. So part of that could definitely explain why we have a bit of like leakage in color. In terms of it being asymmetric, I'm not really sure that there's much of an explanation for that in terms of the penalty. Yeah, you had a question.
So what is E in that equation?
E? So E is the set of edges in the grid graph. So if you think about, oops. If you think about indexing each of the elements of y by 2 indices, so for vertical and horizontal position, then E would be the set of all pairs of one position, say ix, iy, with another position on the grid, I prime x, I prime y, such that either ix is one different from I prime x, or iy is one different from I prime y.
So it's all the points in the, all the pixels in the grid.
These are edges, so I can just write it out for you. So it's either the difference between these two is equal to 1, or the difference between these two is equal to 1. So it's going to pick out any pair of pixels that are either horizontally adjacent or vertically adjacent. Good question, yeah.
What happens if you have just the squared element of that expression? Because it's in general easier to get it close from solution.
Yeah, good question. So if I replace this absolute value by a square, then you're not going to see any 0 differences in the solution. it's going to shrink everything together. So it's going to look like a smooth version of the image. You're not going to see harsh boundaries. The blue's going to fade into the red smoothly. The red's going to fade into the pink smoothly. And everything's going to be more shrunken too. So all the colors will be closer to the center of the scale. Yeah?
I just had a comment on the question we had here about the disk being there in the corner of the pink and the violet versus something. So we actually zoomed into that.
Yeah.
I had a comment about that. So
You know what? Sorry. Maybe we can. Is this if it's not critical to the optimization perspective? Maybe we can just you can ask me after class. These are all really good questions, but I wanted to make sure we got through kind of the rest of the other example and then the kind of content of the convex part of the lecture. So all really good questions. You can come ask me after class. Let me ask just a quick feeler question. Is this a convex problem we've solved? How many people think yes? Very shy in a convex optimization course. How many people think no? OK, so I'd say majority wins. There's people don't want to say yes or no at all. But yeah, this is a convex problem. So hopefully, if I ask you that 2 lectures from now, everybody will be raising their hand in triumph at these kind of questions. So how did I solve this problem? I actually used what you're going to learn and what you may have heard of already as an interior point method. And that's how I solved this particular problem. I used an algorithm called primal dual interior point method in particular. And that's an iterative method. And it required 10 iterations to give me that solution. And that's actually pretty good. I mean, that's actually very, very good. This was not a small problem. So the problem size was 300 times 150. It's not tiny, but it's not huge, but it's not tiny either, right? So that's pretty fast conversions. That didn't take very long at all. It took far less than a second. Here's a different algorithm that I ran. Here's the output I got. Solving the same problem, the same data, the same value of lambda, the penalty parameter, just a different algorithm. I used what's called proximal gradient descent. You'll learn that one actually even before the interior point method. That took 1,000 iterations, not 10, before I quit. And this is what it gave me after 1,000 iterations. It's trying to get to the same solution. So if you evaluate this particular estimate, the criterion value, and this one, you'll see that actually this one is far suboptimal. This is not getting us close to optimality, whereas this got us very close to optimality. So proximal gradient descent actually was a lot slower in its iteration count here. And so after 100 times the number of iterations, it still wasn't very close to the optimum. I tried a third method here just to make a point. I tried coordinate descent on this particular problem. I ran it for 10,000 cycles. So that's akin to about 10,000 iterations of proximal gradient. And it's way farther away from the solution. OK, so this, if you evaluate its criterion value, it's nowhere close to either of the other two. It doesn't even achieve fusion, really, right? It's really very far from optimality. All 3 algorithms were started from the same point as well. They're all given the same initializer. These are all done from the dual problem as well. As we go on and we learn these algorithms, you might come back to this first lecture and say, how do you apply these algorithms to this problem? Well, if you derive the dual of this problem and you apply these algorithms, that's how I got these results. Yeah?
What I don't understand is this is a convex problem, and theoretically, after you get enough iterations to get conversions, you should get similar results.
So the comment was this is a convex problem. So I think what you mean is that there are certain convergence rates we know for each of these algorithms. So I can do a certain number of iterations, and I'm guaranteed to be so close to the solution. Is that what you're saying? So there's 2 different answers that are important here, and it's actually leading into the next point. The first is that they have different guarantees. They don't have the same guarantees in terms of how many iterations are required to get a certain accuracy of the solution. So that's important to know. And the second is that in all of those convergence rates, there are constants that we don't know or that we don't actually care to find in the problem. And there are other issues that actually affect convergence in a practical sense that are appearing in this example. So let's go right into the next slide. What's the right message here? What are we supposed to take away from this? Are we supposed to think that primal dual interior point method is just a better algorithm than proximal gradient and coordinate descent? So no, that's not the case at all. That's not the point we're trying to make, and it's not even true. The real point is that different algorithms are going to work better or worse in different situations. And we're going to learn details like that throughout the course. So hopefully you can the goal is that you can take a look at a problem like this, and without having to actually implement each of these algorithms for this particular problem, you can kind of intuit what's going to work well and what's not going to work well based on what you know about the properties of those algorithms. So here's the explanation for why these worked either well or poorly. The primal dual interior point method was very fast because every iteration could be solved to high accuracy very easily, and it can be performed very quickly. Primal dual interior point method resorts to solving a bunch of linear systems in a row, linear systems of equations. In this particular problem, those systems of equations were very structured. Okay, so you'll see the details as we go along. But it was a sparse structured system of linear equations that it was repeatedly solving. So it was actually a great setting for it. Proximal gradient was very slow because of conditioning. So if we looked at the dual criterion, which was solving, and we looked at something like the condition number of the Hessian, how curved is the dual criterion? It was terrible. So it's actually really poorly conditioned. It means that around optimum, the criterion we're trying to solve is actually not very curved at all. It's very flat. So convergence is very, very slow for proximal gradient, which relies on that. And for coordinate descent, it was very slow because it actually encounters a large active set. That's a much more subtle issue that we'll discuss when we talk about coordinate descent. But when we go to the dual, the effective active set that coordinate descent is using is very, very large for this particular instance of the problem. So it was really slow. Okay, we could change the problem around. We could change minor things about the problem that maybe are seemingly innocuous that could make all of these things very different. So it could ruin the performance of one algorithm or help the performance of another. Okay. So I will usually take a break in these 80-minute lectures, but I think I'm going to just try to go ahead and go through the whole lecture today, maybe finish early, and you guys can go home early. But from now on, I'll take a break through each lecture. I just think that this lecture is it's rather light in terms of content, so maybe your brains aren't quite fried to the point that they usually would be halfway through a lecture. So that was the example of different algorithms performing better or worse, depending on the type of problem we're applying them to. This is the example now of how knowing something about the optimization problem can influence or can affect your statistical understanding of the problem, or whatever the perspective is that you're coming at the problem with. For me, the statistical side or the ML side, but it could be the scientific understanding of the problem if you're coming from a different discipline. So let's go to a 1D version of this 2D fused lasso problem, just because it's easier to portray this phenomenon in the 1D case. So really the same type of problem, except for instead of having an image, I just have data over one dimension rather than two. And let's imagine I have y1 through yn, which are now ordered over a line rather than over a 2D grid. And I also want to form a denoised estimate of those data points, but I want to do so in a way that's piecewise constant over the line. If you think about what we were doing previously, we were getting something piecewise constant over the image. Now we're doing something piecewise constant over the line rather than the image. So to do that, we're just going to penalize the absolute difference between adjacent betas. And by adjacent, now we mean beta I and beta I plus 1. Rather than vertical and horizontal adjacency, here we just have one dimension. So that's called the 1D fused lasso problem, or 1D total variation denoising. And again, the parameter lambda is a tuning parameter. So the bigger we make lambda, the more fusion we're going to see, the more flat pieces, the less breakpoints. When lambda is 0, we're going to see n minus 1 breakpoints, right? Because everything is going to have we're going to estimate beta I to be equal to yi for every I, so it's going to be different for every point. When lambda is infinity, what's the solution going to be to this problem? Just the mean, right? So we're going to have 0 breakpoints. And as we change lambda, we're going to see more or less breakpoints. So for demonstration purposes, I don't know how well you can see the points. Maybe I have to zoom in again. So the points here are drawn in gray. And you can see that I've solved the problem at 3 different values of lambda. This was lambda equals 25. So it looks like there were too few breakpoints. I'm not really doing the right amount of adaptivity here. I'm not really getting an estimate that actually fits the data very well, although it is very fused, has very few breakpoints. This was lambda equals 3.5, so I made it smaller and I got more breakpoints. It looks much better. And this was lambda equals 0.8. So I just chose 3 values of lambda for no particular reason. And you can see that actually there's too much adaptivity. There's too many breakpoints. So one thing that we're going to spend a second looking at is the solution when lambda is 3.5. So let's look at the solution a little bit more closely. And let's note that it actually has a spurious breakpoint, right? All of the breakpoints that appear in the solution here, they look more or less right. And if not, then they're very close. Like there's an extra breakpoint here if you look very, very carefully. But it looks more or less close to the one that should be there, right? This one doesn't. It looks like it's happening in the middle of a stretch of data that should be constant. Why do you guys think that's the case? Why is that there? I think the answer is actually, I would be very surprised if anybody knew the answer, maybe with the exception of Kevin, just because he's thought about this problem in particular.
So why do you think it's spurious?
So if you look at the data, right, it looks like well, I'll tell you, it is spurious because I generated this data from a piecewise constant model where there was just one mean for this whole region. But if you look also, look at the gaps between these segments of data, right? There's a really large gap between each segment, so you'd think that it'd have a much easier job detecting the right breakpoints. It seems kind of mysterious that it actually puts a breakpoint in the middle of a segment that actually has all the same mean.
Maybe because they don't take into account the local minimum at this point.
Local minimum? You mean?
Local is like, then with that lambda interest, in that point it stops looking and taking into account that value to make that average.
Yeah, so that's, I think, the penalty is certainly local, right? The penalty only ever deals with differences of points, of adjacent points, but they're all strung together in the penalty, right? So in a sense, actually, the penalty doesn't really have a local behavior because they're all tied together. This is a very hard question to answer from intuition, so it's kind of a bit hard. The answer is that actually these kind of things always happen with very high probability if you're looking at a sequence of 3 jumps that are all in the same direction. It's a very odd behavior that we wouldn't know about unless we actually knew about the optimality conditions for this problem. So if I have a jump if I have a jump that's, say, positive between 2 segments in terms of the true mean, and another jump that's positive right after that, then it's very likely when I solve this optimization problem that I'll see a spurious jump in the middle segment. The same as if I saw 2 jumps in the same direction that were negative. If I have jumps of opposite signs, it's much less likely. So whoever kind of first thought of total radiation denoising, probably Rudin in 92 is what most people attribute this to. They probably didn't know that, right, when they thought of this. They probably thought this looks like a reasonable criterion. They probably wouldn't know that it would fail almost deterministically when it encounters staircases, something like this. But that we do know now because when we study the optimality conditions for this problem, that kind of comes out of the wash. So I don't know what we'll cover for advanced topics. We may do something like this, although it is a bit more statistical. But basically, when you write down the KKT conditions for this problem, you will see that you can interpret the subgradient at optimality in terms of a discrete random walk. Just comes out of the optimality conditions for this problem. And that random walk typically has a mean, so it has a drift, so it's being pushed in some direction. Here, this random walk, I'm plotting the subgradient, it has a positive drift, so it's being pushed upwards. It so happens, just for reasons when you look at the optimality conditions, that if you look at a sequence of jumps all in the same direction, a staircase, that the mean for that stretch of the random walk is 0. So if it happens to hit kind of the maximum value it's allowed to, which determines the jump, and has a mean of 0, it's very likely to hit the maximum value again, and hence cause another jump. That's going to cause a spurious breakpoint in the solution. So none of that really had to make sense technically. I just wanted to convey to you that this is an interesting example where this kind of failure we only really understand from understanding the optimality conditions of the problem. And if I was, say, a statistician who wanted to kind of categorize the probability of this event, but I didn't know anything about optimization, it'd be very difficult to do so. But optimization kind of opens up that perspective. Yeah.
So there are 2 terms in the optimization equation. One is the distance from the original data points, and the other is the cost of jumping, right? So even if there was not that spurious, wrong, small jump there, and let's say it was like the true data set, the cost will be the same even in that case, right? Because it's the distance between that lower line and the upper line.
Yeah, so I think that's very good intuition. So what you're saying is, if I can relay it, is that the penalty associated with this and with this are the same.
Yeah, exactly.
Because I just add together two
Exactly.
jumps in the same direction, they cost the same. So it's more likely to see this. That's actually true. I think that's good intuition. What ends up happening is something a little bit more deterministic than this, in the sense that
No, I'm not saying that the right one is more likely to happen. I'm just saying that any number of steps can happen, because every possibility will have same cost on the second term, but it will fit to the data more, because the cost to the distance from the data point is less.
well, maybe or maybe not, right? It depends on whether or not the mean of these points is higher or lower than that segment. If the local mean is not, then you're going to fit the data worse.
Yeah.
So I think that's good intuition, but to make that formal, you'd have to understand what's happening with the mean here, right? So it's not necessarily an explanation that we can maybe say be really rigorous about, but I think that's very good intuition. I definitely agree. Right? So if you had a choice between these two in terms of the penalty, you'd wave your hand and say they're both the same, right? Because it's this jump plus this jump, it's the same as one jump. So then it's really the data fitting term that's deciding between these two alternatives when it comes to the optimization problem. What kind of penalty could we use that actually would differentiate between these two, that would make this look worse than this? L2 squared, which one would look worse with L2 squared?
First one. My dad.
This one?
No, the other one.
This one?
Yeah.
This one would look worse, right. So if I square a big number, it gets really big. If I add the sums of squares of smaller numbers, it's smaller. Yeah, no problem. I mean, now we can see that going from L1 to L2 actually wasn't the right answer. How about going from L1 to L0, right? So if we use the L0 penalty, which really just counts whether there's a jump or not. So the L0 penalty would actually add up indicators of whether or not beta I and beta I plus 1 were equal. That would be 2 here, and this would be 1. So actually this would look worse. Why aren't we giving the L0 penalty as the example in this lecture? What's wrong with that choice? Not convex, right? So there's some troubles with it. OK. So now we really just have a few other kind of comments to make about convexity, and then I'll let you guys go a little bit early. The central concept in this course is going to be convexity, as you may guess from the title and the fact that we've hinted at it kind of throughout with examples and stuff like that. Historically, my understanding is that linear programs were the focus on optimization. So people early on, let's say in the 40s and 50s and 60s, they were really concerned with linear programs. And there was a ton of development in terms of the simplex method and other methods for linear programs. And there was some beautiful theory emerging. And then the optimization community asked itself, what's next? What's the next class of problems that we're going to try to solve? And everyone thought that the distinction between problems that were easy and problems that were hard were going to be nonlinear optimization problems versus linear ones. And so people were moving that direction. But very soon, people realized that actually that wasn't the right distinction. There are some nonlinear problems that are very, very hard to solve. And there are some that are much easier to solve. And they actually don't appear to be very different in some transparent sense. The difference is whether or not they were convex problems. And that was the distinction, I think, that is widely recognized today as the right distinction. So convex problems are problems that we can pretty much solve with our choice of algorithm. Non-convex problems are a lot harder. We can say a lot less about them in terms of understanding optimality for those problems, in terms of picking algorithms that are guaranteed to work. And non-convex optimization, solving those types of problems is more like a pick and choose thing. So sometimes I give a lecture at the end of the course which tells you about all the non-convex problems that I'm aware of or that I'm interested of at the time that you can solve exactly. And you'll see if we get to that lecture that it's really just like a bunch of problems that it's a survey of topics. There's not really a principled theme that they follow. Now maybe I'm a bit biased because I don't really do non-convex optimization, and if you take a course from someone else, they'll tell you something differently. So maybe take what I say with a grain of salt, but at least I think it's very fair to say that convex problems are thoroughly analyzable and solvable in a way that non-convex ones aren't. And that's something that is really sold very heavily today when you learn optimization in most kind of standard courses. The two textbooks that will make that point very precise as well that we'll be using throughout the course as supplements will be the Boyd and Vandenberg Convex Optimization textbook, which I think is a really great textbook, and the Rockefeller textbook, which is called Convex Analysis. These books couldn't be more different, to be honest. They present material in like almost the polar opposite way. The Convex Optimization textbook is much longer. It's a much gentler introduction. There's lots of examples. I think it's aimed more at engineering, and it has a lot more of the optimization side of things. The Rockefeller book is really like a math textbook. It's a presentation of convex analysis as a mathematical field. And so in a sense, the Rockefeller book really has a lot more details about convex analysis. So usually the workflow I'd recommend is that if you want to figure something out, go to Boyd and Vandenberg. If you can't find it, then maybe come ask one of us, or the TAs or us, and we'll try to point you in the right direction. If not, go to Rockefeller. It's pretty dense and it's hard to read, but I think it's an amazing resource. You just don't want to open up the book and say, hey, I want to learn about duality, and then have Rockefeller as your first presentation. You're going to suffer through that. But repeatedly throughout this course, if people ask me questions I don't know, I typically go to Rockefeller myself, and it hasn't failed me. So there's a lot of really good material there. But they're supplements, like I said. They're not required. Most of the lectures should be self-contained. And if we have references that would be helpful, we put them at the end of the lectures. So just really basic stuff we're going to finish with are convex sets and convex functions. Just definitions we're going to go through, and then we're going to see why convexity is so important, and then we'll quit. So I think you guys probably have seen this before, but let's just be explicit about it. A convex set in Euclidean space, which we'll call C, it's one that has the following property. If you take any two points, x and y in C, then the new point, tx plus 1 minus ty, has to also lie in C for all t between 0 and 1. That's what it means to be convex. So in other words, intuitively, that means that if I take any two points in the set, and I look at the line segment in between them, that's what this is describing as t varies from 0 to 1 is the line segment in between x and y. That line segment has to be entirely contained in the set. If it's not, if it leaves the set at any point, the set is non-convex. Okay, so that's an example here of this being a non-convex set. What's a convex function? A convex function is one that goes from Euclidean space to R that has two properties. The first is that its domain is a convex set. So we're not going to be very careful with domains in this course, although it's good to be kind of explicit about them at the start. The domain of a function is just the set of all arguments under which it's well defined and finite. So for example, the domain of log is all the strictly positive real numbers, because it's not defined when its argument is less than or equal to 0. Okay, so for a function to be convex, we require that its domain is a convex set. Its domain is going to be a subset of Rn, right? The domain is the set of all x such that f of x is defined and finite and the second condition is the following, which is really the one we tend to remember. Like I said, we typically forget about the domain pretty early on in this course, but technically it's a requirement, which is that if I take the function and I evaluate it at a point tx plus 1 minus ty, that has to be smaller than or equal to t times f of x plus 1 minus t times f of y for all t that are between 0 and 1. So again, this has to do with the line segment joining x and y, but now it has to do with the function values. And actually, this picture says it all. I don't really need to recreate it on the paper. if I look at f of x and f of y, I look at the line segment that joins x and y, then the value of that the function takes on that line segment has to be smaller than or equal to the line that interpolates f of x and f of y. The function has to lie below that line segment. That's the requirement for convexity. Okay, so two simple definitions. What's a convex optimization problem? A convex optimization problem is, well, first of all, an optimization problem we're going to abstract out to be something of this form. We're going to minimize some function, f of x, that's going to be called the criterion function or the objective function, subject to a bunch of constraints. Those constraints are going to be written in terms of functions, because that's the most general way we can represent them. And the constraints will look like gi of x is less than or equal to 0 for all I between 1 through m. Gi are also functions. And hj of x is equal to 0 for j going from 1 through r. These are also functions. And implicitly in the minimization, we're going to only be looking at values of x that are in a set D, where D is the intersection of all their domains. Right? That is just kind of natural that has to be there. We can't ever try to evaluate this optimization problem at a point that's outside of the domains of one of these functions, because then something wouldn't be well defined. So, like I said, D is the intersection of the domains of all the functions that we wrote down. That's an optimization problem. What's a convex optimization problem? It's a particular problem of this form that has the following requirements. F has to be convex, a convex function. Each gi has to be convex. And every hj has to actually be an affine function. An affine function is what you might hear called a linear function in another class. People in convex analysis optimization sometimes differentiate between an affine function and a linear function, but we're just going to write down explicitly what we mean. It means that for constants aj and bj, where aj is a vector and bj is a scalar, we have this form for hj of x. This is called affine. Linear would just be the case when bj was 0. That's just some terminology that people typically use in optimization theory. So that's the requirement for a convex problem. If you have those met, then you have a convex problem. Why do we maintain that hj have to be affine? Why is that a requirement?
It can be divided into two sides. It's less than and greater than. Actually, less than 0 and greater
Right.
than.
So we can always take an equality constraint, right, and rewrite it as a pair of two inequality constraints. Right. So per our requirement that every function in an inequality constraint is convex, we have to have both hj and minus hj being convex. So they both have to be at least curved upwards, if curved at all. Right? So aside from knowing about concavity and more definitions, you can maybe just see that the only function that has the property that both it is convex and its negative is convex are these types of functions. Functions that aren't curved at all, which are affine functions. Okay, so we can see immediately that actually all of the equality constraints in a convex problem are always linear equality constraints or affine equality constraints. Okay, last point we want to make in our first proof in this class is a very important property of convex optimization problems, probably the defining property, I'd say, of convex optimization problems. And that's that local minima are global minima. So anytime you have a convex optimization problem, if you are at a spot where you think you've minimized the criterion because you look in a local neighborhood and you're smaller than everything else you see in terms of the objective value, then that implies global optimality. That means that the function is not going to achieve a lower value anywhere of the domain. That is not true about a non-convex problem, which is why non-convex problems are typically much harder to solve. It's not necessarily true about a non-convex problem. Let's put it that way. So let's be a little more formal about that, and let's actually prove that. We're going to say that a point x is feasible for the optimization problem if it's in the domain of all the functions in question, D, and it satisfies all the constraints. So it just means it's a point x that's in D and that satisfies all these constraints, inequalities and equalities. And we're going to say that it's locally optimal if it's feasible, and it minimizes f in a local neighborhood, which means that if we look at the value of f at some other point y, where y is feasible, and let's say that y is in a L2 ball around x of radius rho, so we just go to x, we make a ball around it, we look at all feasible points in that ball. If f of x is smaller than or equal to f of y for all points y that are in that ball and that are feasible, then x is called locally optimal. Meets our definition intuitively. That actually implies global optimality. It means that there's no other point y that's feasible that has a smaller criterion value than x. Let's prove that. OK, so we're going to actually proceed the proof by contradiction. So let's suppose that, so suppose not. And let's assume that there is some point z. And it has to be feasible, right? Such that f of z is strictly less than f of x. So we were duped. X is not globally optimal. So what's the first thing we know, right? The first thing we know is that actually z has to have a distance at least rho from x. If it didn't, then that would contradict our assumption that x is locally optimal. Now we're going to try to construct some kind of contradiction. So let me draw a picture. That's x. This is the ball of radius rho. We know that everything within here has the property that if it's feasible, f of x is going to be smaller than or equal to the criterion value at that point. And there's some other z that's outside the ball that has a lower criterion value than x. So what are we going to do to try to achieve a contradiction? What's that? Sorry, yeah? Yeah, great idea. So really that's about the only thing we could do, because all we know about convexity so far is stuff to do with interpolation between points. So let's first just knock off a few basic properties. If I take a point tz plus 1 minus tx, and I call that point y, then let's make sure that we understand a few basic things about y. First of all, is y in the domain of all the functions? Is y in D? I see some people nodding. Y is in D, right? Why is that the case? It's because z is in D, and x is in D, and D is actually the intersection of convex sets. The requirement was that every function here were to be convex or more. So that means its domain is convex, and the intersection of convex sets we're going to see is convex. So we have x in D and z in D, so it's any point in between them is going to be in D as well. So we're good. Does y satisfy the constraints? So that actually also is going to be true. Let's just go through them. Let's start with the affine ones. Those are the easiest. Right, the affine ones we just have looking like this. And if we just multiply through, we're going to actually see that we have aj transpose z plus bj and aj transpose x plus bj, each multiplied by some constants. But that's just going to be 0 plus 0. So that's true. And how about gi of y? What are we going to use here? We're going to use convexity of gi to say that this is less than or equal to what happens if we have t times gi of z plus 1 minus t times gi of x, because we know that gi is convex. And that's going to be, again, less than or equal. This is less than or equal to 0. That's less than or equal to 0. T and 1 minus t are both positive because we've restricted t to be in between 0 and 1. So that's met as well. So okay, what we just learned is that if we take any point in between z and x, interpolating, it's still feasible. It still satisfies the constraints. It's still in the domain. So any one of these points is a candidate for the optimization problem. And now let's just take t small enough so that y is in this set. We'll call this set B, this ball. It means that y minus x has L2 norm less than or equal to rho. So I'm not going to go through what value of t makes that true, but you can convince yourself there's actually some value of t that will make that true, just because rho is positive. And importantly, we're going to also take t to be bigger than 0. That's going to be possible with some value of t that's bigger than 0. Okay? Let's look at f now. What happens if I evaluate f at y? I'm going to get the same thing as I got for g, right? Which is that this is less than or equal to t times f of z plus 1 minus t times f of x. That's less than or equal to 0. Sorry. That's not what I meant to say. Which is smaller, f of z or f of x? F of z is smaller, right? It's actually strictly smaller than f of x. T is strictly positive. We know we can take some t that's bigger than 0 to make this in the ball. So this whole thing is going to be actually strictly less than f of x, because I've taken the convex combination of two things, one that's strictly smaller than the other, with a positive weight. So this is going to be true. So that means I'm going to have found some y that's in the ball, that's feasible, and that has a strictly smaller criterion value than x. That's a contradiction. Right, so there we have it. So just to back up, what we've proved is that every local optimum in a convex optimization problem is automatically globally optimal. That'll kind of be a very important fact that we carry with us. So it looks like we actually finished right on time. I didn't give you guys any spare minutes. I will see you guys on Thursday. The quiz we never got to, we're not going to grade it actually. I meant to do the quiz in class. Just go through it for today's lecture. Just get used to the idea of doing a quiz, and then we'll actually grade it starting on Thursday.